Okay, so one thing that I didn't go over, I kind of relied on open math to introduce it. And I find that most people didn't get that assignment done. Okay, or got very little of it done. So I don't know what's going on with, is it because they didn't understand it? It's because it's too simple for them to waste their time on. I don't think that's it for most people, but for some it might be. And, is it just pressure of finals coming up? But anyhow, not everything got done. And only one person got the majority of it done. Actually, maybe two. I think one person here got a little more than half of it done. And they did quite well with it. Okay, well, anyhow, so let's multiply a row by column. Okay, let's multiply the row 5, -3, by the column XY. What do you get? Okay, so first place, at least one person wrote down XY up here and nothing here. Okay, if it was just an XY up here and nothing here, you couldn't multiply it because you'd have nothing to match up with that -3. So you got to have two things to match up. Once we got that straight, everybody pretty much nailed it. Okay, so what this equals is, well, you multiply 5 by X and -3 by Y, you get 5X minus 3Y, and that's it. Okay, but this has to go into a matrix. Okay, so let's put brackets around it, now it's a matrix. Okay. Which row and which column does this go in? It goes in the first row because that's all there is, and the first column because that's all there is. Well, that's what we got here. We've got one row and one column, and there's just one thing in it, which is this product, okay? So with that notation, this is it, okay? Now what's one person I think did was write down 5X minus 3Y twice, but you don't have two rows. If it was 5 -3 and another 5 -3 in the second row, that's what you'd have. But it's only a single 5 -3. So if you go with the idea that the first row times the first column goes in the first row, first column, then since there's no second row and no second column, that's all you've got. Okay, so that's what it is. Okay, and that's easy to understand. It's easy to understand how this goes about. Okay, so now let's try this. 5 -3 multiplied by X, Y equals the matrix consisting of just 7. Okay, now I'm just going to tell you, when you multiply this, what you get is, obviously on the left, you get the matrix 5X minus 3Y. And I should be doing this over here, so I don't block the canvas yet. You get the matrix 5X minus 3Y equals the matrix 7. The matrix consisting of the one expression, 5X minus 3Y, equals a matrix consisting of the one expression 7. Okay. Now, if these matrices are equal, then as you might expect, you can write it without the brackets, because whatever's in the first row, first column here has to be whatever's in the first row, first column here. So there we have it. And that's just an equation. This is just a shorthand way. Maybe it's not even short, but it's a way of writing the matrix, or a way of writing the equation. Okay. So let me ask you, just to make sure we get this. How would you write the equation 3x plus 2y equals 8? Can you write that equation? I'm going to tell you, write it in the form A X equals B. Well, I'm gonna save that, save what I was about to write for the next question, okay? So I'm not gonna tell you what X and B are, because I think you can tell from what you see here what X and B are. And let me make one other comment. This is a big X, it's not little x. Okay, so just to make sure we understand it's different than this X, that this X has nothing to do with this X except that, well, this X appears in the equation, but this X and this X are two different things. Now, I don't know if that's going to help or confuse, but let's see what you do. Now, a little further hint that some people probably need, and I probably should have given it previously. This expression is of the form AX equals B with A, excuse me, equal to 5, your 5, -3 matrix. This X thing equal to column XY and B equal to the matrix of 7. So here's A, here's your fancy X, and here's your B. So how would you write this one? I would say you already done it, but let's check. Okay, now as I hope everybody got it. Yeah, sure. I'm never sure till I see it. But now this, looking, they'll kind of have to compress a little bit though. A is just the 3 and the 2. The fancy X thing is just X, Y. And B is just the matrix with 1 every 7. You might wonder why I don't write this just with a 7. Well, because a matrix times a matrix has to give you a matrix. Okay, so officially, all 3 of these things have to be matrices. Okay. Okay. Well, now let's write this one out now. You read that okay? All right. Everybody says they can, so there it is. See what you can do with that. Okay, now that looks good. Now on the first attempt, some people didn't quite write it out correctly, so let's be sure we understand how to write it out correctly. But everybody pretty much did the right things. But you want to write it out carefully. So if I multiply the first row by the first column, I get 5x minus 3y, and that goes into the matrix. And it goes into the first row, first column of the matrix. Then I multiply the second row by the first column. There's only one column, okay? And that's going to go in the second row, first column. Where's the second row? Well, it's down here below the first row, as you might expect. And where's the first column? Well, it's right here underneath 5x minus 3y. We get 3x plus 2y. And we don't do anything with the 4, 7 because it doesn't say to do anything with the 4, 7. It says multiply this matrix by this matrix, and when we do, we get this matrix. Then, having done this, we use the property of matrices that I'm sure Open Math told you about. And I didn't emphasize it before because until you see why it's true, or until you see how you use it, there's really not much point in seeing it. So anyhow, okay. If these matrices are equal, then the first row, first column of this matrix has to equal the first row, first column of this matrix. Would you agree? Since the matrices are equal, we get 5x minus 3y equals 4. Okay. And the second row, second column has to be equal, otherwise the matrices wouldn't be equal. So everything in this matrix has to equal a corresponding thing in this matrix. So we get 3x plus 2y equals 7. So now we have a set of simultaneous equations that we can express as a matrix product. Okay, now I'd like to go a little further with that. There's a way of inverting the matrix, and for 2 by 2 matrix, it's very simple. So you could multiply both sides of this matrix equation by the inverse matrix and get a solution for xy. Now, if you understand that, great. If you don't understand that, just understand there's a reason that we want to do this, and you might see this later at some point in your mathematical education. We think it's very important that you understand some basics about matrices. Okay, so we have chosen to include a little bit about matrices here at the end of the course. Okay, as a department, we all agree this is important stuff. And it can arise all over the place. So we decide to include it in the course. Okay. We include only as much as we think we can reasonably ask you to do. And when you get the inverse matrices, it's great, it's really interesting, it's really neat. But that would take at least another class day. Okay. So we're not going to, but we are doing this. So if I ask you to multiply a row by a column, well, first place, you check. Equal number of entries in the row, equal number of entries in the, and equal to the number of entries in the column, otherwise you can't multiply them. And I'm sure we'll math quiz you on that. Yeah, not all that sure. But I set the thing up, I'm pretty sure I did. I'm sure I told you that, anyhow. So it's easy to multiply a row by a column, you get a matrix when you do that. Anytime you multiply a matrix by a matrix, you get a matrix, okay? And if you multiply this row by this column, you get the left-hand side of an equation inside the matrix. And if you set that equal to a matrix with one entry, you get this, which gives you an equation. If you have an equation, you can do this backwards. You see what the numbers are here. Okay, now, some people wanted to do an augmented matrix there, but that's not going to work because you got to multiply something by xy. And if you have an augmented matrix, you got 3 things in the row, it's not going to multiply. So just these 2 multiplied by xy equals this, okay? And then if you have 2 rows in the matrix, well, it's pretty obvious if you just avoid the stumbling blocks. So let's just do one more. I don't feel like I'm doing my job unless I strain you just a little bit. Okay, so we're going to do if you can multiply out the matrix on the left and see if you can get some equations. Okay, so did quite well here. We got, okay, first row by the column, 3 times x, 7 times y, negative 4 times z. So it's 3x minus 4y, plus 7y, sorry. No good way to make a 4 into 7. Second row, 5x, 9y, 1z. Third row, minus 2x, minus 4y, 6z. And they're all added. 2x plus negative 4y is just 2x minus 4y, of course. And plus 6z. And this equals negative 1, 3, 5. Now, what's the system of equations? What system of equations does this represent? Okay, so still a little confusion on what we do with this. Well, let's look at what we did here again. We have this matrix is equal to this matrix. If the two matrices are equal, then the first row of this matrix has to equal the first row of this matrix, and the second row has to equal the second row. Well, the first row consists of 5x minus 3y, and the first row of this one consists of 4, so 5x minus 3y has to be equal to 4. Similarly, whatever's in the second row here has to equal whatever's in the second row here. That gives us 3x plus 2y equals 7. So what do we get? What's in the first row here? I asked people to read it to me. They're trying to read it off the board, and I said, no, you got it right on your paper. Read it off your paper. Because they're straining to see the board, okay? Because people try to get as far away from me as possible, and who can blame them? Okay, so whatever's in the first row of this matrix has to equal whatever's in the first row of this matrix. So it's very simple, 3x plus 7y minus 4z has to equal negative 1. Okay, well, there it is. And now, as I was explaining this, everybody was already writing down the second and third equation. Everybody got it right. Okay, second row is 5x plus 9y plus z, and that's going to equal the second row of this, which is 3. So 5x plus 9y plus z equals 3. And then the third row has to equal the third row. Should be obvious now that that gives us negative 2x minus 4y plus 6z equals 5. So this represents this system of equations, okay? And of course, if you started with this system of equations, this is what you would get. It can go either way. And on the exam, there will be questions that ask you to do one or the other. When I say there will be, there's some randomness in the generation of problems. So on many tests, you'll have to do one of these or the other. Maybe with two matrices with 2 rows, maybe with 3 rows. In other words, maybe with 2 equations and 2 unknowns, or 3 equations and 3 unknowns. Now, we're not going deeply into matrices. There are other topics that you've seen a little bit of in open math. We could have 2 equations and 3 unknowns. Okay, if we have 2 equations and 3 unknowns, then you're not going to have a third row, but you're still going to have 2 rows. Okay, if you had 2 equations and 7 unknowns, well, this row would be kind of long. You'd have to have 7 numbers in it. You'd have to have 7 symbols here. Okay, but it wouldn't be any harder. It's exactly the same idea. Then what you do when you reduce the matrix and stuff like that, you know, that gets a little more complicated in those cases. If the matrix isn't square, you can't do its inverse, but we're not doing inverses. Okay, and the inverse of a 2 by 2 matrix is very simple. Inverse of a 3 by 3 matrix, you got to do some row reduction of a different matrix. Okay, and we're not touching that. It's too much. Okay, at the beginning of linear algebra course, a lot of people who shouldn't get weeded out do, because they just can't do the arithmetic. Okay, or they're not dedicated enough to learn. In which case, they probably need to be in a curriculum that doesn't require linear algebra. Okay. Let's see how we're doing. Okay, that's how you move. Okay, Now, some people wanted to start reducing a matrix. Well, you don't do that in this case. If it was two equations and three unknowns, yeah, it'd be appropriate to reduce the matrix. So what matrix would we reduce if we wanted to solve this equation? Well, the system corresponds to the augmented matrix. Well, but there it is, right? And we know how to do the augmented matrix and how to write it down, and hopefully we know how to reduce it. Now, this being the second to the last class, I'm not going to reduce this because I've done a good bit of that. And Open Math is also showing you how to do it. Okay? So we could solve by reducing this. To, I don't know if Open Math. Go Open Math, did you see the word upper triangle? Okay, so I'm gonna put that in parentheses. You haven't seen it, and you don't have to worry about the terminology. Okay, and you won't have to worry about the terminology in the exam. Okay, but I'll mention that this is an upper triangular form, but this is what I've called reduced form. Okay, you reduce the matrix until you got ones and zeros. It's all ones and zeros. The official terminology is reduced row echelon form. You're not, I think, going to see the terminology reduced row echelon form on your exam. Open Math mentions it, so just for Open Math uses the terminology in some of the videos and so forth, some of the materials. So I want to tell you what it is, but it's just what we've done in the case of these matrices. Now, if you got two equations and three unknowns, or five equations and four unknowns, then the terminology becomes more appropriate. And if you have a degenerate system, and a lot of degenerate people around, we might as well have degenerate systems, right? Seriously, a degenerate system, you don't even need to know. Okay, we're not going that deep into it. Okay. Squaring function, exponential, reciprocal.
That's weird. You asked for the toolkit function of the rectangle,
Sorry, I think I didn't hear the word.
squaring one.
Okay. So I'm gonna do that, okay? Something got messed up. Not sure I got this recorded, but we do the rectangle bounded by these, so I'm gonna just go back over this real quickly. Okay, so we sketch X and Y axes. X goes out as far as 11. So I like to go out the powers of 2 because you can subdivide them as many times as you want to. So 2 to the second is 4, 2 to the third is 8, 2 to the fourth is 16. I'll go out to 16. And then I divide that in half, I get 8, divide that in half, I get 4, and halfway between 8 and 16 is 12. So now I've got a scale on my x-axis, and I can draw the line x equals 7. And the line x equals 11, which I labeled x equals 12, which was not particularly astute of me, but that's part of the course. Okay, so x equals 11. Okay, then I do the same thing for y equals negative 12 and y equals negative 4. I'll go all the way out to negative 16 because it's easy to split that in half to get 8 and half to get negative 4 and go halfway from here to here, get 12 without getting any fractions. Okay. So it's the reason I usually use a power of 2. And that'd be 1, 2, 4, 8, 16, 32, 64, 128, etc. So I draw the line y equals negative 12 and label it, draw the line y equals negative 4 and label it. So the next thing I ask is what's the function? Okay. And got the answer, well, squaring function. Okay, well, I think I did that on everybody's paper, but it could have been the exponential, reciprocal, any of the functions. You know how to construct those graphs. So we construct a squaring function inside of this, but it's not going to be inside a 4x4 rectangle. So it's not going to be the toolkit squaring function. Okay. Toolkit squaring function should go here. Okay, here's negative 2, here's 2, here's y equals 4. The toolkit squaring function is always in this rectangle with the red dot here. Now, I think I said in this case, the red dot goes at the midpoint of the lower edge. I could have said the midpoint of the upper edge, but we're going to go with the lower edge. So I'm going to put a red dot here. And because we need the red dot in order to construct the thing. Okay. So now I subdivide the interval horizontally, divide it in half, divide that in half, divide that in half, and divide this in half. Now to do it completely, and I really want to see you do this, I want you to tell me what the equation of these 4 lines are. Okay. Well, this line is halfway between negative 4 and negative 12. That puts it at y equals negative 8. And this line is halfway between negative 8 and negative 12. That's at y equals negative 10. Now, the other 2 lines, I don't really have room to write them here, so I got to go down a little lower. I'm going to say that this line is y equals negative 11. That would be this one. And this last line is y equals negative 11 and a half or negative 11.5. Okay. Now, if you draw a bigger graph and situate it carefully, it's going to be a little easier to label these things. But do your best, because I want to see those labels. I'm not seeing all the labels. Probably going to penalize you for them. Okay. If everything else is correct, I'd only penalize your point. And if it's particularly well done, even though you didn't label everything and everything turns out right, might not even penalize you. Okay. If you make a mistake based on not having labeled things, you know, you're going to pay a little price, depending how bad the mistake is. Okay, so that's what we've got there. Okay, well, now we subdivide here. Of course, you know, the chalk isn't right where I want it to, but okay, this is x equals what? Well, this is supposed to be the midpoint. It's x equals 10. And then I have halfway here and halfway here. And then halfway here. And halfway here. So I've got these lines. Now, they're probably so faint you can't read them from where you are. Because I intentionally made them about as small as I see everybody else doing. Okay, just to teach you a lesson. No, seriously. If I want to make this clear, I can indicate, okay, here. I'm gonna make this a lot bigger. And I'm gonna write out again. Y equals -12, y equals -4. And then I'll do my subdivision lines. Y equals -8. Y equals -10. Y equals -11. And y equals -11.5. Tells me where I am. Okay. Now I've got my red dot in the middle of the bottom. Edge. And I've got x equals 10 here. And x equals 12 here. So that through the red dot, I've got x equals 10. This is x equals 8, not 10. Okay, this should be x equals 8. Then I can divide this half in half. Divide this half in half. And this is what I mean by the usual algorithm. You've got an algorithm for doing most any of these toolkit functions, and you got to know what it is. And of course, everybody learned that very early in the course. So you got to make sure you remember. So this is going to be x equals 11 here. And this is going to be x equals 10.5 here. And over here, we're going to get the x equals 9 line. And halfway between 9 and 10 is the x equals, no good place to label that one. X equals 9.5. Now we follow the algorithm to sketch our curve. You should have another color handy. I do right here in my hand. Okay, so we start upper left-hand corner. Move 1 to the right, 2 down. 1 to the right, 2 down. Include the red dot. Make it symmetric. And there we have points that we can use to construct a pretty good graph of a scoring function, but it's not the toolkit scoring function. We still use the same algorithm. Anytime we've got a rectangle, we can sketch a parabola inside that rectangle using the algorithm, and we do a pretty good job of it. Now, up here, and I'm not going to do the construction lines. This is the toolkit scoring function. This, I'll sketch here. This is too small to really do a good sketch, but. There it is, roughly. Okay, so what's this? Well, this is the toolkit squaring function after transformation. So what transformations do we use? Okay, so here's the construction. So here's the construction. Of our transform squaring function. Down here and over here with a little more detail. But now we see it in perspective with the toolkit squaring function. Okay. Now we want to know what the transformations are. We want to identify the transformations. And once we've identified the transformations, we just use the AF of x minus h plus k. And we can write out the formula for the function. Okay, so we identify our transformations. Let me solve enough room here. Still not. Make sure the left-hand side of the board's visible. Okay. Okay, identify the transformations. First, identify the vertical spread. Okay. Well, what are the dimensions of this rectangle? What are the dimensions of this rectangle? They're 8 by 4, aren't they? Well, can you see? How far is it from here to here? How high is this rectangle? It goes from y equals negative 12 to y equals negative 4. Okay, so I can put in parentheses negative 12 minus negative 4 is 8. And what about the x? From 8 to 12 is 4. So clearly, let me bring this back over here a little bit because we have to solve this. Okay, here's x equals 8. Here's x equals 12. How far is this? 4. Okay. Here's y equals negative 4 and y equals negative 12. Let's extend these lines a little bit. How far is this? It's 8. Now, to give you big numbers, you can't just count from negative 12 to negative 4, right? You go negative 12, then negative 11, negative 10, negative 9, negative 8, negative 7, negative 6, negative 5, negative 4. Okay, that's 8. Whatever happened to my fingers. I was getting choked up over it, so I kind of lost track of where my fingers were. Okay, get the idea? It's an 8 by 4 rectangle. That tells you. And what's this? This is 4 by 4. What do you have to do to a 4 by 4 to get an 8 by 4? You got to stretch it double this distance. Okay, in any case, I write this down. Let me kind of circle this in this one in purple, and this one in green. This indicator goes with the green projection lines in the purple. Okay? Make sense? Okay. So we've got an 8x4 rectangle. Well, if we divide this dimension by this dimension, we divide 8x4, and that tells us how much we have to stretch this. Because if we stretch it double, we get 2 times 4, which is 8. Okay, so there's our stretch. So g of x is AF of x minus h plus k with a equals 2. All right. Now, since I'm using the notation f of x and g of x, okay, squaring function is going to be our f of x. And our transform squaring function is g of x. So here's g of x. And of course, here's g of x in a window that allows us to see what's happening between x equals -8, x equals 12, and between y equals -12 and y equals 4. All right. We still have to estimate h and k, but we don't have to estimate. Okay, now I ask you what's a horizontal and vertical shift, and people are looking at the x equals 8 line and the x equals 12 line, and oh no, whoa. Suppose the x equals 7 and x equals 11, isn't it? X equals 7 and x equals 11. Here I've got x equals 8 and x equals 12. Well, I'm sure you're used to downright ignorance by now. Not ignorance, carelessness, I know. But I don't always see it. Okay, so I kind of got to change all my x's here. This is supposed to be x equals 7 and x equals 11, which means that number is going to change, and this number is going to change, and this number is going to change, and things are getting all smudged out. So what am I going to do about that? I got to fix those smudges a little bit. Otherwise, you won't be able to read it. Okay, so yeah, try to unsmudge this and this. I think I'm making it worse. Come on. Stuff on there. Okay. I should probably have the camera off. We'll live with it. Okay, here x equals 7 and x equals, that should be in purple. Well, here it is, x equals 11. And here again, x equals 7. And then x equals 8 here, and x equals 10 here, and x equals 9.5 here, and x equals 8.5 here. Also, we got labeled as x equals 10 here. The halfway point is x equals 11. Unfortunately, I did try to label my x's. X is not 11, x is 9. Yep, I didn't change that one. That x should be 9. And this x should be 9. Okay. X equals 9 on this center line. And of course, x equals 9 here. All right, again, I was blocking the board for a lot of that. It just, I labeled this 8 and this 12 because it's 4 units between 8 and 12. I wanted 4 units, but I got the wrong numbers. Had the wrong numbers floating around in my head, my fault. But center here is x equals 9, halfway between 7 and 11. And halfway between 7 and 11 here is again x equals 9. And these other coordinates I think are correct now. Okay, so now we want to see what happens. What's the horizontal shift? What's the vertical shift? Focus on the red dot. Goes from here to here. Okay, what are the coordinates of this point? Okay. What happens to the red dot? Well, it moves from 0, 0 to 9, -12. Did I get that right finally? Okay. So 0, 0 to 9, -12. So you show with your fingers what the new horizontal shift would have to be. We want to go from 0, 0 to the point down here, which is 9, -12. So how far do we have to go in the x direction? You got that thumb tuck? Yeah, 9. You clearly did. That's good. Okay, so horizontal shift is and that's h. That's what we subtract from x to shift our coordinates. What's the vertical shift? Now, you don't have enough fingers. Okay, first answer, probably one I would have given if I'd have been out there, is 12. Well, no, it's -12, right? It's important whether we go up or down. Okay. You get out of your chair and get confused whether you're supposed to go up or down, you might end up on the floor. Okay, so the direction is important. Okay, well, you're not going to get confused on that. Okay, equals -12. Okay. So Talk isn't writing very well, but what's the formula for g of x? Can you write it out? Okay, now at this point, everybody wrote it out correctly. It's AF of x minus k, but now we've identified A here, Put a little circle around that. And we've identified H here, and we've identified K here. So A is easy to identify. If you have the dimensions of your new rectangle, you just divide by the dimensions of your, the vertical dimension of your toolkit rectangle. And you get 8/4 equals 2. If the height was 6, you'd have 8/6, which is 1.5. No, it isn't, it's 1 1/3, 4/3, okay? So forth. Okay, so we get that, and then we just ask ourselves, well, what has to happen for the red dot to get from where it is to the midpoint of the lower or upper width edge of this rectangle? And you find that it's gonna be, well, H is gonna be the x coordinate. Since you're starting at x equals 0, to get to x equals 9, you gotta go 9 units. You're starting from y equals 0, you gotta go -12 units to get here. So that you can just read that right off of the graph. If you've labeled it, if you've labeled everything, then you're gonna know what the coordinates of the red dot are. And you're gonna be able to tell me what H and K are. So A is 2. I'm gonna write it with F's. I'm gonna just write out this form literally. Now K is -12, so I'm gonna put a -12 there. Now, what's that? Do f of x minus 7 minus 12. Now, only now do we have to go back to what the original function was, right? Well, the toolkit squaring function f of x we know to be x squared. We didn't even need x squared to do the construction. The construction's there floating around the universe even before we invented numbers. It's always been there if you ask Platonists. Okay, and I tend toward that perspective. Okay, this whole form, this whole geometric form precedes numbers. Okay, even before the decimal system was invented, people were doing constructions. The Egyptians did it. They didn't have our number system. They had a pretty good one, but it wasn't quite as versatile as ours. Okay, so again, f of x equals x squared. So f of x minus 7 in this case is x minus 7 squared. So right there is our formula. Of course, we need a parenthesis around this. Now, if f of x was the toolkit exponential function, then we'd use most of the same subdivisions. We wouldn't have used these two lines, but we would have used these and these. And we wouldn't have needed the 9.5 or the 8.5. We'd have gotten a point here, 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 and here, and we'd have had the exponential function. Okay? We'd have had an exponential function with a new asymptote. If it was a reciprocal function, well, our rectangle's a little different, but it would have been okay. So what can we do with this? Okay, g of x is 2 times the quantity x minus 7 squared minus 12. Well, we can check and see if this really represents our function. Like, we've got this point here. What are the coordinates of this point? Okay, well, x is 8.5 on this line. I had it pointing to this one. I keep making mistakes. I'm sorry. Okay. But x equals 8 is this line, so this point has x coordinate 8. And y equals -10 on this line, so it has y coordinate y equal -10. So this point is -10. Right here. We're gonna check. X equals 8, do we get y equals -10? Well, let's see, g of 8, replacing, it's we can put y equals for any function, right? So y equals g of x. If x is 8, what's y? Is it 10? -10? Oh, g of 8, that's gonna be 2 times 8 minus 7 squared minus 12. That equals 2 times 1 squared minus 12, which is 2 times 1 minus 12, which is 2 minus 12, which is -10. Yep. This should be convincing evidence that these transformations work as advertised, which is the reason I've been emphasizing this so much during the whole course. Okay, one more. Is a vertex at 9, -12. Well, the easy way to say is that's vertex form. This is vertex form. And the vertex is not at 9, -12 because the horizontal shift isn't 7, it's 9. Did I do that up here too? Man. H equals 9. What did I write? 7. It's actually 9. It's just that the loop is a little bit linear. Okay, I can make that correction. Okay. It is 9. Of course, does that change my result here? Well, if this is 9, then this is 2 times the square of -1, but the square of -1 is 1, and it doesn't change anything else. Okay? Got to change this 7 to a 9. Bad looking 9, but it's more like a 9 than anything else. So, okay, so is the vertex at 9, -7? Okay, I'm going to stop there. We're going to pick this up in class. Because we're going to say more about this, and we're going to go back to the whole idea of constructing the graph of a square, of a quadratic function. And going to try to pull all that together. Okay. Okay, now again, we are going over what is already on the video. But if you want to start here, if you can understand it quickly, that's fine. If you already understand it, and know everything, that's even better. But we start with the rectangle bounded by x equals 7, x equals 11, y equals -12, and y equals -4. Okay? How do you do that? Well, you set up your coordinate axes. And if you want to see this done, you see all the details of doing it, just go back to the beginning of the video and watch it. But I think most of you are going to understand what I'm doing here. Okay, so what we do is we just start with the coordinate axes and we draw the line x equals 7. Well, first we got to put a scale on it. So I choose to go out to 16. I'd like to use 1, 2, 4, 8, 16, 32, 64, and so forth, because you can always divide into lots of times, okay? So I start with 16, divide that in half, I get 8, divide that in half, I get 4, and halfway between 8 and 16 is 12. And that gives me enough information to locate x equals 7 and x equals 11. And x equals 7 is going to be right here. I take the interval from 4 to 8, divide it into 4 equal pieces, and there's x equals 7. Okay. And over here, same thing, the interval from 8 to 11, divide it up, and I find from 8 to 12, I divide it up and I get x equals 11. So I've got these two vertical lines, x equals 7 and x equals 11 right here. Okay. And they're going to be part of the boundary of the rectangle that I'm going to get. The rectangle also runs from y equals negative 12 to y equals negative 4. Well, again, I go from 0 to negative 16. Divide that up, get negative 8. Divide that, I get negative 4. Halfway here is negative 12. And now I've got the line y equals negative 12 and the line y equals negative 4. You notice that I've labeled these lines. I keep telling you, you need to label these lines, okay? Label the things so you understand the coordinate plane better and you're more familiar with it, because that's going to be important, as important pretty much as anything else in this course. And I find that people are still a little bit shaky in some of this, okay? So you really need to be able to follow these instructions and so forth. Okay, well, there it is. Here are the two vertical lines, y equals 7, x equals 11, two horizontal lines, y equals negative 12, y equals 4, and you take the rectangle that is bounded by those lines. It's a rectangle just sitting there smiling at you right in the middle. The only rectangle on the screen if you've done the construction up to here. Now, later on, I went ahead and constructed the 4x4 standard rectangle. Okay, but we don't need that at this point. We're just following the instructions. So we do the rectangle bounded by these lines. Again, if you want to see that constructed in detail, go back and look at it. Okay. Or start at the beginning of the video, but you might not need to go all the way back to the beginning. Now I construct it again because the next instruction is going to be use the usual algorithm to construct the graph of the squaring function. Okay. Well, it's a little hard to do here. I did it. You know, I split this rectangle, I divide it in half vertically, divide that in half, divide that in half, divide that in half. The usual thing that you know how to do and have known how to do for close to 3 months now. Okay. Yeah, probably for 3 months. So you got to know those algorithms. You got to know the algorithm for doing the squaring function, exponential function, reciprocal function, etc. Okay. So there it is. Now over here, I do it again because it's bigger and I can label it and you can actually see it. I almost intentionally did this too small for you to see everything, to show you that sometimes you got to show them in a large picture. Or if this was out at x equals 207 and 211, and y equals negative 512 and negative 504, you wouldn't be able to even draw your x and y axes and still have this rectangle big enough to be visible. So we could just draw this rectangle out here in space without drawing the x and y axes. Okay, if it's too far. Now, it's good in this case to do it with the x and y axis, and sometimes I'll ask you to do that, but you can always sketch it again big. Okay. You can space these lines any way you want as long as you label them with the right numbers. So I draw two vertical lines, label them x equals 7 and x equals 11. I've done what it says. I just don't have the x and y axis in this picture. Okay, and I can draw two lines for y equals negative 12 and y equals negative 4. Now you want negative 12 lower than negative 4, you know that. But you want to exercise that knowledge just to get you more familiar with the numbers. So there it is. There's a line y equals negative 12, the line y equals negative 4. Okay, the line y equals negative 4. Okay, now I do the subdivisions. Okay, vertically, I divide the rectangle in half to do the squaring function. Then I divide that in half, I divide that in half, I divide that in half. always going toward the edge with the red dot. And there's a red dot there, it's kind of gotten obscured by everything. And it's got coordinates too, and we'll see in a minute what the coordinates are. Okay, so halfway between -12 and -4 is -8. Halfway between that and -12 is -10. Halfway between that and -12 is -11. Halfway between that and -12 is -11.5. You gotta reason that out. You know, that's why I say, figure these out. Draw the lines, then put the coordinates on them. It gets you more familiar with the coordinate system. It makes it easier for you to visualize what you're doing when you analyze a function, which is what this course is all about. If you don't have the numerical, then you're kind of handicapped. You're just, you know, throwing symbols around a piece of paper without any real good idea of what they mean. You can learn to do that, but it's easier to learn if you can do the numbers. Okay. And it sticks better. You do all the steps. Okay, well, again, you understand, once you do all the steps and once you label all these lines, can't do that. Give it a try, send me a copy, come see me. One way or another, let's get it straight, okay? All right, now, we then divide it vertically. We're doing the squaring function, so we start with the middle line, and then we cut this right rectangle in half, and then cut this rectangle in half with two more lines. And then we do the same thing on the left. You know how to do that. Doesn't matter how big, how fat or skinny your rectangle is, you can do that. Okay. You can also use different scales. So, you know, it doesn't have to, your rectangle doesn't have to look like its actual shape. You can still draw it and label points. So if you wanted to make y equals -12 here, and y equals -4 here, and y equals 7 over here, and y equals 11 over there, you could do it. Of course, you wouldn't want to do it. You wouldn't want to overlap this graph. You understand? I can make that rectangle any dimension I want, as long as I have the right numbers in these, it's going to work out. Okay? Okay. So one way or another, you get this rectangle down here, and now you label the coordinates. Now we talked about the y coordinates, the x coordinate. Got 7 here. I've got x equals 11 here. Halfway between is x equals 9. Halfway between 9 and 11 is 10. Halfway between 9 and 10 is 9.5, and all that stuff. And I label all these lines. So, two things on the homework, it shows me that you understand, okay? And on a test, it gives you points of reference. And if you haven't labeled it and make a mistake as a result, well, and it's going to be a little harder than just if you make a mistake, okay? If you got it labeled and make a mistake, I'm more forgiving on mistakes, depending how bad the mistake is, okay? And everybody's going to make mistakes. It's not going to be a trivial test. But this process is one that you should be able to do for sure. Okay. Having done that, I follow my algorithm. I start in the upper left-hand corner. It's the algorithm for the squaring function, right? Start in the upper left-hand corner, go 1 right, 2 lines down, 1 line right, 2 lines down to the vertex, and then keep everything symmetric on this side, and there's my parabola. Okay, so I sketched the parabola in here. Now sketch the points. Okay, I also sketched the toolkit squaring function because we're going to need that as we move on. I know the coordinates of these points. If I want the coordinate of any one of these points, it's easy to read. What's the coordinates of this point? Well, it's on the line y equals -11.5. It's on the line y equals 9, x equals 9.5. So this point is 9.5, -11.5, right? This point, which we're going to use, is a -10. Why? Because it's on the line x equals 8 and on the line y equals -10, right? Now, one other thing I'll say, if you read the stuff earlier, I kind of screwed up some of these numbers. When I did this, I used 8 and 12 instead of 7 and 11. Because I had those numbers in my head after doing the Ys, and I didn't think. Okay. I think I had them right here, but when I did this, I kind of screwed it up. So if you see something that doesn't seem right, you're probably right. But by the end, I had it labeled correctly, and I just now warn you, okay? Unfortunate that I did that, but it's what it is. Okay. Now, next thing we want to do, there are two things we've done so far. We've constructed the rectangle. Okay. Then we've constructed the transformed squaring function. That's over here, okay? In other words, we constructed a squaring function. It's not the toolkit squaring function because it's not in this rectangle, okay? Now, for perspective, here's our toolkit squaring function in this rectangle, okay? Here's the transformed function that we constructed in this rectangle, right? We want to get the equation for this function. Well, we know that we transform the toolkit squaring function by vertically stretching if necessary, and then horizontally and vertically shifting, right? And we know then that that gives us the equation of the form, where the heck is it? Down here somewhere. Okay, well, it's going to be here. Okay. G of x is a f of x minus h plus k. We've done a lot with that. Last week, we talked about solving the equation a f of x minus h plus k equals some number, right? And for all the various squaring functions, which pretty much goes over most of the algebra and requires most of the algebra you need in this course. So make sure you're good with that. If you aren't, ask me questions, whatever we can do to get you straight on it. Okay. And review. Okay. Okay, so we identify our transformations. We're going to want to find the equation of this function. So our next step is to identify the transformations. And we start by identifying the vertical stretch always, because it always comes first. Okay. You got to do the vertical stretch before you do vertical shift, or you get something terribly wrong. All right. Now you could actually do a horizontal shift before you do the vertical stretch, but just do the vertical stretch first. It avoids confusion. It's always first thing I recommend that you do. Okay. I'll also mention the horizontal compressions. I'm not going to test you in horizontal compressions. Okay. If you get this beam down, I'm happy. If you know it well enough, you'll be able to figure out horizontal compressions if you ever need them, and you might not. Okay. Okay. They're important with exponential functions. They're important in second semester pre-calculus when you do the trig functions. Okay. I'm going to leave it to those courses. Okay. First, identify. I hate to leave it out, but we've spent a lot of time remediating stuff because of things that don't get covered in the prerequisite courses. It's one of the sacrifices we make. Get this down. That's not bad. Okay, so anyway, as for the 16th time, we're going to identify the vertical stretch. We're really going to do that now. Okay. How do you identify the vertical stretch? Well, you look at this rectangle, you look at this rectangle. Is this rectangle vertically stretched from this one? Yeah, you got to stretch this rectangle out to get this one. Okay. So, how much do you have to stretch it out? Well, you got to get the dimensions of this rectangle. What are the dimensions? What by what? Okay, you want to tell me? How high is this rectangle? Can you show me with your fingers? And what goes from y equals -12 up to y equals -4? How far is that? It's 8 units, isn't it? Okay. And what's this? This is a 4x4. Okay. How do you go from a 4x4 to an 8 by something? You got to vertically stretch. You got to double its height. It goes from 4 units high to 8 units high. Okay. Now, you can do that by calculation, but I say, well, say it's 8 by 4, let's just concentrate on the 8. It's 8 because vertically it goes 8 units to meter. And to calculate that, if you got big numbers, you just subtract where you end up from where you start from where you end up. Okay? It's where you end up minus where you start, -12. Yeah, I did that backwards. Keep discovering mistakes. I don't know who keeps making these mistakes, but I can fix them. Write that down quickly. No excuse, I should have written it down correctly. It's -4 minus -12. Okay. Where you end up minus where you start. Okay, well, again, you can use common sense and figure that out. Now, how wide is it? Where's from x equals 7 to x equals 11? That's 4. Okay, and I'm not going to mess with the width of these rectangles. I'm going to keep them 4. Now, say you had a rectangle of width 2. And apparently that's a mistake I made when I gave you the assignment. You can do it with width 2, but you're not going to get the right equation. Okay. And I'm not going to talk about what you have to do there. Although you've been over it, you've done homework on it. We're not testing it. We're not emphasizing it. Okay. So it's 8 by 4. Okay. And again, why 8? Because vertically it goes from -12 to -4. So we do -4 minus -12. Horizontally, it goes from 7 to 11. I wrote this down before I discovered that mistake. Should be 11 minus 7, it's still 4. So our vertical stretch, vertically we go from 4 units to 8 units. We divide 8 by 4, just divide the vertical dimension of this one by the vertical dimension of the toolkit. Square the 4 by 4 square, and you get the vertical stretch. So now we've identified the vertical stretch, and we know that A is the vertical stretch in this form, because A is multiplied by whatever your original y coordinate was. Okay, so there it is. So A is 2. Now we have to figure out what H and K are. Well, that's really easy. We simply ask ourselves, what happens to the red dot, right? Well, where does the red dot start? Starts here. We transform it. Okay, so we stretch this thing out so it looks like this, and then we move it over here and down here, right? So the red dot has to move how far horizontally? Can you show with your fingers? Should be obvious. Has to move 8 units, right? Okay, I think that's 8. That's our 9. 9. Right. Don't believe me. Correct me when I'm wrong, or at least question me, okay? We got to move 9 units. See that 8 there, you know. Anyhow, we got to move 9 units because why? Well, we look at the coordinates here. 9, -12, right? So we move from x equals 0 to x equals 9. Our horizontal shift is, well, we're shifting from 0, 0 to 9, -12. Horizontally, we're moving from 0 to 9, so h equals 9. Horizontal shift. Vertical shift, we go from 0 to -12. Well, that's a shift of -12, and that's k. So there's h and k. Now we plug in h and k. Here's our formula for our g of x function. We plug in for a is 2. We plug in for h is 9, so h becomes 9, and k becomes -12. We rewrite it without all the red and stuff, 2f of x minus 9 minus 12. And now we go back to what the toolkit function was. As I commented, we didn't even need to know that this is a squaring function. But that this was the x squared function. All we needed to do was follow the algorithm for the squaring function, which never mentions x squared. Okay, the algorithm never mentions x squared. It just says this is what you do for a squaring function. Okay. Now that we've followed the algorithm and identified our vertical shift and stretch, our shift, vertical stretch and our shifts, we remind ourselves that this is the x squared function. This is the first time we've used the fact that this is x squared. We've used the fact that it's a squaring function. We've never said, well, that is x squared, but we know that. Okay, so at this stage, we change, well, f of x is a square, so f of x minus 9 is quantity x minus 9 squared. And we've been over and over how you do function notations. I'm not going to take time to talk about that anymore, so make sure you understand it. We did it pretty thoroughly last week once more. Okay. Had this been the exponential function, then what would I have done? I'd have gone from here, from this point to this point, to this point, to this point, to this point, and I'd have the exponential curve, right? Okay. And then when I got to this stage, I'd have used 2 to the x instead of x squared. And f of x minus h would have been, f of x minus 9 would have been 2 to the x minus 9. And I'd have the squaring function, the exponential function, as it would be constructed in this rectangle, right? Okay, so it's all there. All right, now it's a squaring function, and I want to use the squaring function, so I want to go on with this. I'm going to clarify this. It says, so y equals g of x. It looks like soy equals g of x. So let me separate my SO from my y. My niece's husband, nephew, in Michigan. They got 60 acres, he's a big deer hunter. Okay, so does food plots for deer. And one summer I was up there, said, hey, want to go to supply store? So yeah, it's always good to take a ride. And so I got to get some sowies. I got to plant the sowies. So, well, geez, what do they feed deer in Michigan? Sowies? What's a sowie? It took me a while to figure out who's saying soy. But it took linear algebra. I had a professor. He wasn't bad. He presented things well. I'd never learned much from seeing people talk about it. I dug it out of the book. Worked out for me to an extent. And he talked about the dignity of the equation. He had an accent. He did, his first language certainly wasn't English. And you could pretty much understand most of what he said, but what in the world did diggity mean? There's a song. You ever heard the song? Hot diggity, dog diggity, boom, what you do, you know. Everybody knows that song, right? Well, that was a big song back in the late 50s. Okay. Back when I was too young to understand really what you do. Anyhow, I got older pretty quick. But anyhow, so I'm thinking for half the course, I'm wondering what this diggity was. It's the degree of the equation. You know what the degree is, but do you know what the diggity is? What does diggity have to do with linear algebra? Okay, and digression. Well, I said regression, and probably that too. Okay, so here we got it. Now, okay, we've done all this. We've got our minds clear now. We've got this function. Okay, and that function represents this curve or this curve. This is the bigger version of this because we've labeled where it is. We don't need to know where the origin is. Okay. do need to know where the origin is, like if we want to find the x-intercepts, we're gonna have to extend this a little bit. All right, well, we're gonna check this because we have the point 8, -10. It's right there on the graph. And it says that if x equals 8, this curve, the function that represents this curve should give us -10, right? So if we plug 8 into this, we should get -10. You want to really understand that. Otherwise, well, you want to really understand that so you understand what a graph is telling you. So you understand what a function is saying, because that is going to be important if you go further in your math, any further than just a statistics course. A statistics course, I can talk. Okay, right? So if you go on to second semester pre-calculus, you don't understand these things. If you go on to calculus, you're going to want to understand these things. You're going to want the mathematical sophistication that you get by thinking through this and understanding it, okay? It's going to serve you very well, I think. Okay, well, at least in my fevered brain, I think it should serve you well. Let me know if I'm wrong. Okay. If x equals 8, do we get y equals -10? Because this says that the point 8, -10 should be on the graph, which is the same as saying that if we plug in 8 here, we should get -10 here, because this is y. All right, well, we do that. We plug in x equals 8. And the arithmetic is really easy. 8 minus 9, as most of you suspect, is -1. And if we square -1, you know darn well it gives us 1. So we end up with 2 times 1 minus 12, which is -10, so that checks. How simple. Okay, now understanding that these symbols go with that picture, that's not simple. That's why we've been emphasizing the meaning of the picture the full 14 weeks of the course that we've had so far, okay? Or maybe this is a 14th week. So we've had 13. Now we get to another question. Is the vertex at 9, -12? Is the vertex of this thing at 9, -12? There are 2 ways you can answer this. One is, well, yeah, this is in vertex form, and there's the coordinates of your vertex. It's 9 and -12. But if you don't know what the vertex form means, well, another thing you have to be able to do is you have to be able to find the vertex thing. Now, there's a technique for finding vertex form called completing the square. And I've made the executive decision for this course, and as I'm teaching it, I don't teach completing the square. I should. There are a lot of things we should do that we just can't do. I regard that as something you can learn easily if you learn this course well. Okay? And you've seen it. Open Math has used it. So when you see it again, if you see it again, which you might not, but if you see it again, you'll be able to do it. As long as you understand factoring and the distributive law and stuff like that. It's not that hard. Okay. So how do we find the vertex? Well, using the methods that we've developed, if we forget, let me just show you the easy way. Well, that is the vertex form. That's the way the textbooks have done it. That's what you used when you did homework. Okay. But you might not remember it. I'll try to reinforce it, so maybe you will remember it, because it might do good. You don't remember or recognize that? Okay. You expand it to general form and find the vertex, negative b over two a, plug that in, you get the y coordinate. Remember that? You want to, because one thing I guarantee you're going to see is you're going to have to take a quadratic function in general form and graph it by transformations. Okay? And to do that, you're going to have to find the vertex. Or complete the square. I mean, if you prefer to complete the square, that's great. I'd find that wonderful. But it's easy enough to find the vertex, and you're probably going to choose that. Okay, so I don't have much room, but it doesn't take much to do this. I got this thing up here. They sell these things with a label on them that you can't get off. So when you paint over the label, it's all screwed up. I'm gonna go ahead and do this. Okay, so well, I'm expanding this. I'm not going to use this because the chalk kind of gets messed up. You're going to get 2x minus 2x squared minus 36x. And then it's I think it's plus 69. Okay, I'm going to check myself. I'm going to plug in x equals 8. No way I'm getting negative 12 out of it. Maybe I am. 2x squared is 128. 128 and 69, everybody knows, is 197, I think. And 36 times 8 is 288. 197, 288. There's something wrong. Never done anything wrong before, so how could this be? I mean, if I square this, I get x squared minus 18x. And I double that, I get 2x squared minus 36x. And I square, oh, got to double that 9 when I square it. So I need another 81 on this, which gets me up, I think, to 160. You don't know all that. That's just what's going on in my feeble head here. And then I get 288, 200, and why can't you people do arithmetic? Somebody's screwing up here. Okay. Yep, 162, and that should be 150, not 160. And now if I plug in 8, I get what I should. And if I plug in 9, oh, wait a minute. Don't need to fumble with these numbers on screen. Okay, I apologize. Something my brain's misfiring here because it still doesn't seem right. And I'm doing too much in my head. And my head isn't up to it right now. So if remember vertex is at x equals negative b over 2a, and how that fits into the quadratic formula, so you don't have to remember anything. Okay? Yeah. Recording. Okay. Well, that equals negative 36 over 2 times 4, which is negative of negative 36 over 2 times 4. That comes out negative 9. And that is, of course, where the vertex should be. The y coordinate. You just take this form and plug in 9, because the x coordinate of the vertex is 9, the y coordinate is going to be whatever you get when you plug this in. So if I've done this correctly, 2 times 9 squared, I'm sure is 162. 36 times 9, I think I might have been multiplying 36 times 8, and I should multiply by 9, but I'm not sure. It's 270, and 54 is 324. $162 and 150 is 312. Right, kind of small. Okay, that does come out and it checks. Now you probably can't see from where you are all the arithmetic, but you see what I've done. I've expanded this thing into this form. And now I can remove the question mark because that does prove to be correct. Okay. And I've then found the vertex by the negative b over 2a. Negative b being that negative b in your quadratic formula, the 2a being the denominator in the quadratic formula. As I've emphasized a number of times, to make sure you either memorize an extra equation here or just understand how to find it within the quadratic formula that you need to know. Okay. So we get the x coordinate of the vertex, and it comes out -9, so that agrees with the graph that we've constructed. Then the y coordinate of the vertex, you plug in the x coordinate and you get the y coordinate. Okay, that's all you need to know. And you get the vertex. So now you can construct the thing because you know that the horizontal shift and the vertical shift are 9 and -12. And this is not -9. Okay. We have the negative and the negative there. That makes sense? Does that look familiar? Make sure it is. That's the whole thing. That's at section 3.2, I think. Okay. It's kind of a key to understanding a lot of what follows that section in the text. All right. Now I want to go back and do something about matrices that I didn't get to do last week. Now, what you should know from what we did last week is how to multiply a row by a column. So what do we get if we multiply this by this? Not going to take the time for me to have you write it down and everything, because there's a lot of other stuff we want to go over that should be helpful to you. Okay. But do you see what it should be? You have an opinion? Well, it's going to be first times first, second times second, right? And that's going to give 5 times x and -3 times y. Okay. Now let's take this. Now, the row times the column is the same as it was up here. So we know this is going to give us 5x -3y. And there's nothing to do with this. It's just there. So we get 5x -3y equals 7, but we get the matrix 5x -3y here. Okay. So we get the matrix 5x -3y, which is why we had to write the matrix 7 here. Because when you multiply a matrix by a matrix, you get a matrix. Important idea that we discussed to some length. Non 20 minutes or something. Okay, in a different class. If this matrix equals this matrix, then the only thing in this matrix has to equal the only thing in this matrix. So 5x -3y has to equal 7. Okay. But this is saying something different than this. It's saying this is a matrix and this is just an equation. This is a matrix equation. This is just an equation. Now, we ask, okay, take the equation 3x plus 2y equals 8. Can you write it in this form? Well, yeah. And I say write it in the form a times big fancy x equals b. Okay. where the big fancy X isn't this little x here, it's a different X. It's a standard notation, and you can see it on the exam. So something like this could be asked on the exam. So can I write this equation in this form? And the answer is yeah. If I do this, but just like what I have here, except I've got different numbers multiplying the X and the Y, 3 and 2 instead of 5 and -3, right? So you want to digest that. So if you're not digesting it right now, go back and look at the video, digest it, or look at Open Math, get it digested, okay? And for anybody who wasn't here when I said it, I did extend the assignment that was due today through this Friday with a note to really best if you get it done by Thursday for class, okay? Just better for you. It's fine with me either way, except it's better for you. So it is finer if you, for me, if you do it in time. That might or might not be feasible, it depends on your schedule. Okay, so this translates to this. Now, what does this do? Well, how do you multiply this matrix by this matrix? You multiply the first row by the first column and put it in the first row. You multiply the second row by the column and put it in the second row, right? That's the procedure we developed last time, and Open Math is going to tell you the same thing. So when we do 5 minus 3 times xy, well, that's just what we got here, isn't it? It's going to give you 5x minus 3y. Where do we put that? It came from the first row in the first column. There's only one column, so it had to be the first column. It came from the first row, so it goes in the first row. And then we do the 3, 2 times the xy. We get 3x plus 2y. That goes in the second column because it came from the second column of the first matrix. And that's got to equal whatever's over here. We haven't done anything to what's over here. Now, what does that translate to? Well, very simple. If this matrix equals this matrix, then this has to equal this, and this has to equal this. That should be obvious. But if it's not, ponder it, look back at what we did, because we developed it and explained this more slowly and in more detail in the support course, okay? But it's going to give you 2 equations then. If this equals this, well, we get this equation. And if this equals this, there's an equation. So this represents this system of equations. Now, there's a reason for that I talked a little bit about. We're not going to do it. It goes beyond what we have time to do in this course. But you can do the inverse of a matrix. And it's easy to do the inverse of the 2 by 2 matrix. I'll give you the rule and you can do it, you can multiply it and learn it, but we need another class to cover it and make any sense out of it, okay? But if you multiply the left side by the inverse and the right side by the inverse, you're just left with x, y equals 2 numbers. So you know what x is and you know what y is, and you've solved the equation. And that's how computer algebra systems actually do it, sort of. A lot of times they use reduction of an augmented matrix. So anyhow, okay. Well, now can we write this system? Or can we write this matrix product? Okay, by the time we got to this in the previous class, everybody was doing fine with it. Okay, everybody's able to write it out. So if you're not understanding it, go back and look at the development or get it out of Open Math or read your book. Okay. But we multiply the first row by the first column. 3 times x there, 7 times y there, -4 times z there. This row by this column goes in the first row and the only column. Okay. Then we do the second row and it goes in the second row. We do the third row, goes in the third row. This doesn't change. But now we say, well, first one has to equal the first one, second one has to equal the second one, third one has to equal the third one, and we get 3 equations. Okay. Now that can also be very handy if you're using Desmos or Wolfram Alpha or something to solve a matrix equation, to solve a system of equations. It's very easy to translate the system into a matrix equation. And then through that matrix equation into the computer, press a button and there's your solution. Okay, you should know what's going on if you're going to use it in any sophisticated way, but for most applications, just being able to translate between this and this is going to allow you to solve just any matrix equation, any system of equations. Okay, so it's very, very useful, which is, again, what we've chosen to cover. The system doesn't require that we cover this. It's a decision of the math faculty. We're unanimous. Yeah, this is important. We've covered it before. We need to put it back into the books. Believe me, it's good stuff. It's important stuff. And this translation is maybe the thing that's going to be most useful to you in subsequent courses, if it comes up. Okay, and it might, because this is linear algebra, one where the guy kept saying diggity when he meant degree. Okay. I can't pronounce his language right either, so we're even. I haven't ever tried, but I don't think so. Okay. I'll say one more useful thing about this is that this system corresponds to this augmented matrix, right? You do the augmented matrix of this system, that's what it is. Okay. So we could solve by reducing this to, now I said upper triangular form, but that's not a word that anybody recognizes. Anybody recognize upper triangular form? So it's simple. It's a very simple idea, but we don't need it. Okay. Reduced form. Does that ring a bell? I mean, I talked about reducing the matrix, right? You reduce it till you got ones and zeros. Okay. So, but your text and Open Math will also talk about reduced row echelon form. And that's the official name for the reduced form. That's the official name for what you get when you're done reducing the matrix, like we did last week. Okay. So when you see reduced row echelon form, I mean, all those words confused me when I was taking a much, much higher level course. Okay. I was much, much smarter than I was in my sophomore year than I was my freshman year. And I just didn't like the terminology. Okay. And figure out what was going on, why they calling it that. That always gives me trouble. So if that reduced row echelon form doesn't resonate with you, just think reduced form, you're reducing the matrix, okay? And don't worry about the terminology because in this course, it's not going to do the form. Okay? You just think reduced form. In later courses, if it comes up, at least something in your brain will remember having seen the words and connect it maybe with what we did. Okay. Okay, that's it for those. For matrices. Okay. So get it done. Okay. Now we handed out some sample problems that type might occur in the test. Everything we talked about can occur in the test. Okay. Stuff that we went over with the transformations is one of the big things. You're practically guaranteed to be asked to do something very much like what we did there. Okay. Just as you're practically guaranteed to be asked to construct the graph of a quadratic function using transformations. Okay. Okay, so how many of you have a question in the first one? Anybody have a question how to do that? And now what I'm going to say is this evening, try to find time to go over the whole thing because some of you are reading it very meticulously, and email me with the number of the problem and briefly what it is you're not sure of. Okay. So nobody, okay, number one, you're just gonna, number one, I'll show you here. And I'm not gonna write the problem down, I'm just gonna say, okay, here. You start by graphing an exponential function. Okay, then we vertically stretch this thing by a factor of 0.4. Okay, so this is 4 by 4. We stretch it down to 1.6 by 4. Throw our exponential function in there. By 1.6. It's 0.4 times 4. And then we raise it up 4 units. So then we take this graph and raise it up 4 units and take this whole rectangle, raise it up 4 units. Turns out it's going to be there. And there's our function. Okay. So think about that. Second one. Well, we just did that. So you might still have a question on it. So you might want to work through the homework assignment, and then you should be good there. Third, anybody have a question on the third? That looked pretty familiar. Okay, I'm going to tell you. Okay, this is the first problem. Third problem, I'm going to say we do first row plus 3 times the second row, third row plus 2 times the second row. Gives us two equations and 2 unknowns, which we know how to solve. That's how you solve a system of 3 equations. You then proceed to solve the system of 2 equations. But everybody did real well on that, so I'm convinced everybody should be in pretty good shape on that. Find the inverse function. Anybody have a question on that one? I'd say most of you should have a question on that one. Okay, so quickly. Still got 6 minutes. You got y equals 4 log of 3x minus 5 plus 9. And it says f of x equals, but that's y. What do? Switch x and y, you get x equals 4 log of, it's log base 2, of 3y minus 5 plus 9. Okay, so now you got to solve this for y. Well, you subtract 9 from both sides, you get, and I'm going to put the log over on the left side. So we got our y here and our x over here. And now we got 4 times the log, but we have to have just a log. We got log base 2 of 3y minus 5 equals x minus 9 divided by 4. So all I've done at this point is I've just subtracted that 9 and divided by 4. So I got log base b of a equals c. Okay. Log base b of a equals c, so b to the c equals a. Until I got it down to this form, it was not in this form. We didn't have just a log base b of something. We had something in front of it and something attached to it, okay? But now it's in this form, so I can write it in the form b to the c equals a, which is just 2 to the x minus 9 over 4. Equals 3y minus 5, and now the y isn't trapped inside the log, it's out here. And I can just add 5 to both sides and divide by 3. So we get, should have left my y on that side, or never mind. We get y equals 2 to the x minus 9 over 4 plus 5, all that divided by 3. And that could be simplified a little bit, but I'd accept that for this course. Okay? I'd be even happy if you simplify it. But all we did was we switched x and y, and then we did what we know how to do to convert the log form to the exponential form. Just make sure you're good with that process. We got bugs in the windshield, want to write a linear function, right? Well, this was number 4. Number 5. I'm just slopping these down anywhere. Why is the number of bugs? And we got the time in years. Okay. I can do this easily enough. I can say that years since 1990. Okay. Now we translate the information. We say that we have 8,000 milligrams in the year 1990. Well, in the year 1990, the year since 1990 is 0. So that means we have 0, 8,000. It's actually bug mass on the windshield. Okay, you don't remember, but back before the 90s, if I drove 400 miles to, family in Ohio, I just might not be able to see out the windshield with that many bugs. Now you don't see many. There's big changes going on. Okay, anyhow, we got that. And then we say in the year, I have my glasses on, 2016, which is 26 years after this, I've got only 2,000. Y equals 2,000. And I'd like to see these lines. It just means that you're learning more if you can do this. So I got 2 lines, now I find the linear function. Find the linear function. To do the fundamental triangle. Easy to do with these points. I've got 26 here. I've got negative 6,000 here. All my arrows. The slope is then negative 6,000 over 26, which should be reduced. And I know my y-intercept. So that y equals negative 6,000 over 26 times t plus 8,000. I can reduce that. You can use decimals. And then you can answer questions because you got a function. So if I ask you how many bugs in 2003, well, that would be a t for 13 because 2003 is 13 years after 1990. You plug in 13 for t and you get the number of bugs. If I ask you, when is the number of bugs down to 3,000? You plug in 3,000 for y and all for t. And those are easy solutions. Okay, we're going to do more of this next time, but please tell me which problems you want to see and what you want to see about them. We're going to have to do it quickly, so you're going to have to refer back on the videos. We don't understand everything. I try to say everything on the videos, so you have what you need.